Yeah, maybe. Ah, sorry, there is some. Maybe. That's good. Okay, thanks. Sorry about not looking properly. Okay, so we were talking about non-singular curves, and we had shown that the local ring of a curve at a non-singular point is a discrete variation ring. So let me repeat this. So curve for us was a variety of dimension 1. And now I first want to remind you the definition of a discrete variation ring. Definition. So A is a local ring with maximal ideal M. And we will also assume that A is an integral domain, no zero divisors. So A is a discrete valuation ring, which is always abbreviated like that. If first M is maximal, M is a principal ideal, so there exists some element T such that M is generated by it, and T is then called uniformizing parameter. Obviously, there's more than one uniformizing parameter. If you multiply T by any unit, it's also a uniformizing parameter. And second, for any uniformizing parameter, we can write every and all. We can write every element A in A as A is equal times U times T to the n, where U is a unit.
Every non-zero?
What?
Non-zero, A must be non-zero, right?
Yeah, that was you. You asked the same question before, and
yes.
The answer was the same. As A times U times U, where A is a unit in A, and n is some positive integer, non-negative integer. And then what we had shown is that that was a theorem. If P is a non-singular point on a curve C, then the local ring of C at P is a discrete valuation. Okay, so that's where we were. So that this holds. Now, one could wonder why it should be called discrete valuation ring. It should have something to do with the valuation. So now I want to define the corresponding valuation and then use this in some way. So, definition. So we take again P, a non-singular point on a curve. Then define a map, nu P, from the local ring at C at P without 0, as always insists, to the non-negative integers, which sends nu p of f is equal to n when f is equal to u times t to the n, where u is a unit, and you know, t is a uniformized parameter. We had seen that this number n is independent of the choice of uniformized parameter, because it actually just means that f is in the maximal ideal to the n. Okay, so this is, and this is evaluation, a non-Archimedean evaluation, namely it follows the following properties. So nu p satisfies the following. So first, the valuation of the product is the sum. Second, if I want to look at the valuation of the sum, this is bigger or equal to the minimum of the valuations of nu p of f and nu p of g, and with equality if these two numbers are different. And the last thing, that f is a unit in this local ring if and only if nu p of f is equal to 0. So this is in some sense related to the talk of Rossi. So one can, you know, this valuation, if you then associate whatever 2 to the, you know, x to the nu of p or something to it, you would get a norm, and this would be a multiplicative norm according to this, and this statement would be a non-Archimedean norm, like in his talk, and so what he had was also generalization of this. Okay, so these multiplicative semi-norms that were in his talk are also just generalizations of the things you associate with non-singular points on curves. So in some sense, you can view them as generalizations of points on curves. Okay, but I mean, we are not going to pursue that in any way. So let me check these properties. So let's prove that. So obviously, so I put f equal to a times t to the n, g equal to e times t to the m, where a and b are units. Then, if I take fg, so if I take nu p of fg, this is nu p of a times b times e to the n plus n. Okay, so this is true that it's additive, because you can see it. Second, it was just we assume that which one we want, n is smaller than equal to m. Then f plus g is equal to a t to the n plus b t to the m. This is equal to t to the n times a plus b t to the m minus n, and this is non-negative. So we see this is an element in the local ring, so the valuation of it is bigger or equal to 0. So it means that the valuation of this is bigger or equal to n. Which is the first statement here. And if this inequality is strict, then we get that a, and I claim that a plus b t to the m minus n is a unit. You know, in the same way as before, if it was not a unit, I could then it would lie in the maximal ideal, and this thing lies in the maximal ideal, so I could subtract it, and so A would lie in the maximal ideal, but we know that A is a unit. So by trivial arguments, this is a unit, and thus we see that this is a unit times t to the n. So ut of f plus g is equal to that. So if the valuations are different, then it is precisely the minimum. If they're equal, it could be that there's some cancellation. And the third statement is obvious. No? If you have a unit, no, you write it as a unit. So we're actually not so much interested in this valuation, but we want to extend the valuation to the function field. So we want instead the valuation on KC. So we can extend mu p from O CP to KC, but obviously this is without 0, and this is also without 0. And this is as follows.
Just, I have a question regarding notation. So before talking about terms, our notation for the function field was AX.
No, that was for the coordinate ring.
Ah.
I always wrote K for the function field. So we want to, so this is the definition. Note that the function field of the curve is equal to the fraction field of the local ring of X with P. Now if you just think of it, before you take the fraction field of AX, which is the set of all quotients f divided by g of elements in AC. AC lies in OXP, so we therefore get, if we take the fraction field of OXP, this could in theory be bigger. But the elements here are also just quotients f divided by g, where now f and g are themselves quotients. So quotients of quotients are quotients. No? So this is, it doesn't get bigger if we do it twice. And so therefore we can extend nu p from OCP to 0 to KC. No, I'm going to say it. I don't know, was this clear to everybody? Because I just said it, but I'm not sure whether everybody was obvious. So an element here, so KC, is a set of all f divided by g if f and g is in AC or something. Or if you are in the affine case, assume we take the affine chart and then whatever. So it contains as a subset this set OCP. So these are certain quotients. And now if I take the quotient field of F, it contains this, but so it contains this like this, but AC is contained in it. And every element like this. But anyway, now then we just take, so if I take K, the quotient field of OCP, this is just the set of all F divided by G divided by G divided by H, H divided by K, where these are elements in the quotient field, which both of which are defined at P. And obviously, this one can write as F K divided by GH. So it's just again an element in KC. Just so it doesn't get if we do it twice, it doesn't make a difference. So now let's take an element there. So how do we extend it? So we say mu P of F divided by G, where F and G are in OCP, is just defined to be, what would you think? It should be, it's supposed to be multiplicative, so the only choice that we have is we take the difference. So mu P of F minus mu P of G. We could, it doesn't. So, and this is well defined. If P of if F divided by G is equal to F prime divided by G prime, then this means Fg prime is equal to G F prime. That's what it means that they're equal. And so mu P of F plus mu P of G prime is equal to mu P of G plus mu P of F prime, which precisely means that mu P of F prime divided by G prime is the same. Okay. So we have this extension here. And one can say a little bit more. Namely, so let's maybe first kind of try to give some kind of intuition for this. So that's how we think of it. So we think of it if mu P of some rational function is equal to some number n. If the number n is positive, we say it has a 0 of order n there. And we also think of it, it does vanish there, and the order is this mu P is the order to which it vanishes. And if this number is negative, we say it has a pole, and the order of the pole is minus mu P of it. So I just say, and it also, so this is how we call it, but it's also the correct equation. That's what actually happens. So for instance, if we work over the complex numbers, then these things will be meromorphic functions, and this mu P will actually precisely the order of pole and 0. So it will be precisely that. So there's nothing, so corollary, no. So I say that let n equal to mu P of F, for F in KC without 0. So we say, so if n is bigger than 0, we say F has a 0 of order n at P. If n is smaller than 0, we say f has a pole of order minus n at p, which is now a positive number. And if n is equal to 0, then it has neither pole nor 0. So the corollary, which is mostly a corollary to the definition, but also to what we saw for this valuation on OCP, is that that again P is not single point of the curve C. And so first we can extend the way we had defined it before. So this thing is compatible with the way we had defined before the valuation, namely, so if f is a rational number, a rational function which is not 0, then nu p of f is equal to n. So I maybe should say, maybe let me, so I didn't say it explicitly, it's clear from what I wrote here. When I extend it, now nu p is a map from kc without 0 to the integers. So if we have this, nu p of f is equal to n, this is if and only if we can write f is equal to u times t to the n, where u is a unit. Okay, so the same thing for positive numbers we had this before, and the second statement is that OCP, so the local ring of C at P, consists precisely of the elements f in, so first we have 0, union the set of all f in KC without 0, such that nu p of f is bigger or equal to 0. So we can characterize to be in the local ring by this valuation. Okay. So this is, both of these are trivial, but we want to X it out. So nu p of f is equal to n, if and only if we can write f as a quotient of two elements in the local ring whose valuation such that the difference of valuations is n. So that means we can write f equal to, say, u1 times t to the l divided by u2 times t to the m, with l and m. No? And the difference, n, is equal to L minus M. That's the definition. Then obviously we can divide. No? That means f is equal to u1 divided by u2, or if you want u1 times u2 to the minus 1 times t to the L minus M, which is f. And the product of two units is a unit, and this is this. So we see L u1 u2 to the minus 1 is a unit. So we see that that's fine. And for the second statement, we know by definition if f is in the local ring, then by our definition we have that nu p of f is bigger or equal to 0 by definition. Now conversely, it's almost the same. So if mu p of f is bigger or equal to 0, then it follows that f is equal to u times t to the n, which n bigger or equal, so it's equal to n bigger to 0. Then this is equal to this. This is a unit in OCP, and this is also an element in OCP, so T is in OCP. So obviously this lies in OCP. So it's standard triviality from the definitions that the local ring consists precisely of the elements of positive, of non-negative relation. So I want to give one small geometric application of this. Namely, I want to show that if I have a morphism from a non-singular curve to a projective, no, a rational map from a non-singular curve to a projective variety, it always is a morphism. So it cannot be that a morphism is defined almost everywhere on a non-singular curve, but there are some points where it's not defined. If it's defined to an open set, it will be defined everywhere as a map to a projective variety. This is something very special about, and we'll make a few comments about that later. So theorem. So let's see a non-singular curve. Y, a projective variety, and say phi from C to Y, a rational map. Then phi is more. I should actually say, so this is something, it's actually, it turns out to be, I mean, we don't see it here, but it's a very useful result. It plays a big role in many things. So, I mean, for one thing, more generally, one has what is called a complete variety. We know that projective varieties are complete. So it is if you have a complete variety and a rational map to a complete variety, then it will be a morphism. And in fact, what one can really prove is that the variety is complete if and only if this holds. And this is, in many cases, the way how you check that. And so, actually, if you want, so it's very often, so complete is kind of the first step to prove that something is projective. And so for many spaces which you construct in an abstract way, the way to prove that they are projective is by checking this. So it's very important if you do moduli spaces. So moduli spaces are things parameterizing, spaces parameterizing something. And so the idea is if you can define the something almost everywhere on the curve, you can, if you then can define it everywhere, then it means the space parameterizing these things is complete. And then with a little bit of extra work, it is projective. Okay, so let me see. And so, for instance, it means if you have a morphism from a curve minus a point, you can always extend it to the missing point. This is something which in Hartshorne, in a different formulation, is called the evaluative criterion for properness. Which is something which, when I first looked at it, I thought was a totally terrible thing, but it's basically this statement. So let's try to prove it. So Y is a projective variety, so we have Y lies in some projective space, Pa. Okay, so if phi from C to Pn is a morphism, so we have here, we have a rational, so if viewed as a map to Pn it was a morphism, then if I take the inverse image of Y, this is, an open subset. This is the where, so, this means there's an open subset of C which maps to Y. An open dense subset of C. So that means the inverse image of Y contains an open dense subset of C. C is irreducible, so that means phi to the minus 1 of Y must be the whole of C. No, because C is irreducible. So that's the first thing. Now, therefore, we just have to extend this rational map to a morphism to Pn. Then it automatically will go to Y. No, that's enough to extend. So, or we could also just say thus we can assume Y is equal to Pn. Okay, because if you have if it's extended as a morphism to Pn, it actually maps to Y. So morphisms to Pn we know are given by tuples of rational functions. So we can write phi equal to this equivalence class f0 to fn, where the fi are elements in Kc which are not all 0. And the equivalence class means the same map is defined by multiplying every single element by the same rational function. And the morphism, the map is defined as a point P if I can find a representative, so that not all of them are 0 at that point, and one of them, so that all of them are defined at that point, and at least one of them is not 0. So we want to show, so now we take a point, let P be a point in C. We want to show that it's defined at this point. If it's defined at every point, it's defined. So now we can use our uniformizing parameter. So let T be a uniformizing parameter at P. So that means it lies in the local ring, and that's the maximum idea. So we write Ni equal to the evaluation at P of Fi. And now we obviously these are it's a finite set of integers, so we can take what is the minimal or the max. So we can take the smallest of these numbers. So choose I0 such that Ni0 is equal to the minimum of the Ni for I equals 0 to n. And then we put Gi for all I, we define this to be fi times t to the minus I0. What do we have then? Then mu p of gi is bigger or equal to 0 for all I. That means all gi are defined at p. Because that means they are in OP. No? And mu p of gi0 is equal to 0. That means gi0 at p is different from 0. No? The units are the elements which are not 0 at that point. So this means that if I take this phi, which is equal to f0 to fn, it's also equal to g0 to gn, because we have done this, and it's defined at p. Okay, so we can use this uniformizing parameter to kind of remove all the zeros and poles, and so we have this thing. So if we only do this for curves here, but one can do something similar for higher dimensional non-singular varieties, where you replace points by subvarieties of codimension 1, and then you also can get some kind of a similar thing, and this would then, for instance, lead to a theorem which says that if you have a non-singular variety of dimension n, then every rational map is defined outside a closed subset of codimension at least 2. Okay, so a similar proof, if one would have set up the corresponding thing, which is more difficult, would prove that. So generalize in this way, but at any rate. So as I said, remark in particular if we have a morphism phi from the curve minus a point to y, which is projective, then phi extends to p. And you can interpret this, and this is what I was trying to say in the beginning, you can interpret this as saying that there's no point in y missing, or you can somehow go to the limit as the points in C go to p. And there will be a point there, which you can map to. And so this is why this is some kind of completeness result, so it shows that there's no point missing. So this somehow says there is no point missing in y. And as I said, it's equivalent to the completeness, and you really need that y is projected. So this is the result from default false if y is not projective or C is single. So you cannot, if P would be a singular point of the curve, then you might not be able to extend the map. And we really used here, it's non-singular because we used the local count. So if it's not projected, you have, for instance, just the map, you have the inclusion from A1 to A2, if you want to view this as P1 minus the point infinity, you could say you have a morphism from, so just I, which sends just the point A to, say, A, 0. So obviously this cannot be extended to P1 because we know any morphism from P1 to A2 will map the whole of P1 to a point. So we cannot extend this map from P1 minus infinity to P1. Okay. So in particular, so as a corollary, we also find any two birational projective curves are isomorphic.
So what if our rational maps the curve to an affine variety? By considering this affine variety to be inside Vn, can we get the same conclusions? It will extend to a morphism?
Well, to the projective thing, to the projective closure, yeah, but not to the affine variety. We know that if you have something from a projective thing to an affine thing, it always has to map everything to a point. There's no non-trivial map. But obviously we can extend it to a map to the projective closure, because that's part of what we said. Okay, so this was as much as I wanted to say about this in general. Now I come to this last chapter of the. So we want to use a little bit of this to talk about curves in a more geometric way. So we want to study non-singular projective curves, and the main tool we want to use is so-called divisors, which are formal linear combinations of points with. So this last chapter is a bit different from the others because I don't try to prove everything. There are a few things which I will have to be a bit more sketchy to just give the ideas. It's not, but I want to at least say definitions properly and tell you some of the results. I don't know how far I will get because I have only how many lectures? 2.5?
3 lectures including this.
Yeah, so that means 2.5, yeah. And so, so let me, but I hope I will be able to say something interesting. Okay, so we talk about so this is, if you wish, about curves, non-singular curves, and so we want to, so want to study curves by using divisors. So now we'll actually first have to tell you what the divisor is. And so for us now in this whole chapter, a curve should be equal to a non-singular projective curve. So we will only consider non-singular projective curves. And so I just say curve to mean non-singular projective. Like before, when I say ring, it means a commutative ring with one. So, okay. So first I want to define what's the divisor. It's the following definition. So it's just a formal sum of points in the curve. So let's see the curve. And the divisor on C is a formal sum so D equal to sum over all the points in the curve AP times the point, where AP is an integer and only finitely many AP are non-zero. So you can, if you want to say it in a slightly more formal way, it's a map from the points of the curve to the integers, which is 0 for almost all, for all but finitely many points. So to every point in the curve we associate a number, which is this AP, and except for finitely many of the points, this number will be 0. So this is some formal thing. Okay, it's a bit like, you know, it's as abstract as polynomials. So it's not such a formal sums one that we consider all the time. So if we have two divisors, so BP are divisors, we can form, for instance, their sum, and we can also form the negative, and the difference. So we have D plus E is defined to be sum P and C, AP plus BP times P, and D minus E is equal to the sum of all P and C, AP minus BP times P. And so we can also form minus E, which is just the sum of all minus B times E, and clearly, so thus clearly the set which I call div C of divisors on C is an abelian group. With whose zero element is just the zero divisor. No, everything is zero. Is sum over all P in C, 0 times P. No, that's not very surprising. So we are in the moment we are kind of dealing with some kind of trivial abstraction. But we will see that these things are actually useful. And this divisor, obviously, I will usually call 0. So obviously it might be sometimes more practical to just mention the points where this is actually non-zero. And so we introduce also another notation where we only keep those. So we also write D equal to A1 P1 plus A R PR for D equal sum P in C, whatever EP times P with such that EP is equal BP. So for all P, EP is equal to the sum over all I such that Pi is equal to P of AI. I just write like this as a sum. And most of the time, obviously, we might want to assume that these points are all distinct, in which case we can just write it. Okay. So this is situation. And now what do we, so we can now also define, a few words for it. So for a divisor, D equal to sum P AP times P, we can define a few things. So, and the point Q in C, the multiplicity of P at Q is nu, I mean the same, I use the same notation as for nu Q of P, which is equal to, obviously, just a Q. No, just the number which is there is the multiplicity. So the degree of D is the sum of the multiplicities. Which is an integer. And I can also talk, maybe I might also need it, so the support of D consists of all the points where the coefficient is not 0. So of D is the set of all P in C such that AP is not 0. These are all very simple concepts, but quite many. But we just want to formally compute with this. And finally, so we will denote. Yeah. So we have this degree. So we call div D. We don't pick it. Div D of C is equal to the set of all divisors. So D, which are divisors on C, such that the degree of D is equal to D. So this is the set of divisors of degree D. And note that div 0 of C is a subgroup of div C. No? Because just if the degree is additive in, if you take the sum of two divisors, the sum, maybe I should actually say this, it's clear that if you wish, if you want to say it in a fancy way, we have that.
This is a homomorphism.
Yeah. So the degree from the div of C to the integers is a surjective homomorphism. With kernel div 0. Oh, clearly that is the case. Okay, so much for this. So now, until now, obviously you cannot possibly hope to get from something as abstract as this any useful information. If you just formally sum the points, we are just doing nothing. So it is totally impossible to imagine that without doing anything more fine, we would ever get anything useful out of this. So we have to somehow, make this interact with the geometric structure of C. And so the first thing that we look at is the divisor associated to a rational function. And so if we these somehow are some special divisors, and so they tell us already something about the geometry. And so these are called principal divisors. You see, it might or might not look imposing to have this abstraction, but obviously it contains no non-trivial information, so you cannot possibly do anything with it. But now we want to somehow be able to encode some geometry into these divisors, and then maybe it will become a useful way to, to have something surface about the geometry, which one maybe wouldn't be able so easy to see directly. So principal divisors are the divisors of rational functions. So what does that mean? We have this multiplicity of a rational function at a point, and we take just these multiplicities to define divisor. So definition, let H be a rational function on C, again, must not be 0. The divisor of H is, notes I wrote it with H like this, maybe I find it easier to write it like this. Diff of H, which is the sum over all points P and C, the multiplicity at P that we had just defined in terms of the valuation of H times P. So divisors of this form are called principal divisors. So maybe we have to worry a little bit that this is a divisor. So that means finitely many of these numbers, only finitely many number of these numbers should be non-zero. So this is a note. If H is a divisor, because we can we know, so H lies in case C, so it follows we can write H equal to F divided by G, where both F and G are elements in the homogeneous coordinate ring of degree D for some D. And you can see if you have, so this is the class of a polynomial of degree D. So if you have a class of a polynomial of degree D, which does not lie in the ideal of C, and this you have here, so obviously they are both non-zero, then they have only finitely many zeros on C. So both F and G have only finitely many on C. And so it follows that F divided by G, so if a point here, if a point in P in C is a pole, then it must be that G has a 0. And so there can only be finitely many poles. If a point is a 0 of H, then F must have a 0. So there can only be finitely many zeros. And so there are only finitely many points, and so it follows there are only P and C with mu P of H is different from 0. And obviously at each local ring, at each point, this H is an element in KC without 0, you see? So we know that mu P of the thing at the point is some integer. So this is fine, some finite integer. Okay, so this defines it as the divisor of a rational function is a principal divisor. Yeah, we come and we want to now see that principal divisors, what do we want to show? We want to show that these are a subgroup of the divisors. Namely, we can say it as follows, with the following remark. So by what we have shown before, we know so let H be an element in KC without 0, and P in C, then we know that, so F and G, then we know that nu P of F times G is equal to nu P of F plus nu P of G. This is true for all points. So this means so if this statement says that nu P, that the divisor of F times G is equal to the divisor of F plus the divisor of G. No? Because the divisor is just the sum over all points, nu P of it times this, so it just adds up like this. So in other words, this div, the small div, from the function field without 0 with the multiplication to the group of divisors of C is a group homomorphism. So here the divisors, obviously with the addition, is a group homomorphism. Okay, and so the image is a subgroup of it, so that's the principal divisors are a subgroup of this C. Okay, so we find this nice subgroup. I mean, I hope you understand. So here we we send F to the divisor of F, and then this statement says it's a group homomorphism. Okay. So, so now I want to introduce a very important event of the curve, which is the Picard group, which is the this group of all divisors divided by the subgroup of principal divisors. Yeah. So the Picard group. So until now, soon I come to a statement that I will not prove, but first, so let C be a curve. So two divisors. So first I make this definition. I can say it in different ways, but I want to introduce all the words that are used. So C is a curve. So two divisors, D and E, are called linearly equivalent so if their difference is a principal divisor. So in some sense, you could say that you somehow think that these divisors coming from a rational function I somehow consider as the trivial ones, and so I want to always compute modulo them, and I want to see how much there remains. So if one if I wanted to scare you, I would say that, if I want to say it in a more fancy way, so if I take the group of divisors divided by the principal divisors, that actually is the same group as the group of invertible sheaves on this thing. And so, what we are doing here with this story with the divisors is somehow that we do in a simple case, or we study in a simple case what one would study in general using homology of sheaves. But here one can do it in elementary terms without, if one talks about curves. If one, just in terms of divisors, linear equivalence, one doesn't have to know what a sheaf is and things like that.
What's a sheaf?
Well, I just told you don't have to know it. But so, you really want the definition now?
No.
Yeah, no, I can give you the definition. But I mean, obviously it doesn't play a role here because I've avoided doing it. But, so it's just something, it's a very general notion, just as an aside. How much? So it's something to generalize in some way the notion of functions on some space, say continuous function, differentiable functions, regular functions, or more complicated things. And so what it really is, but this has nothing to do with what we do here, no? So X is a topological space. So let's say I talk about a sheaf of abelian groups, for instance. So I always have to say what you want, but say a sheaf of abelian groups. So a sheaf. So first I have to tell you what a pre-sheaf is. So this is something which wants to be a sheaf but doesn't quite succeed. So a pre-sheaf of abelian groups is a map which I call F, which goes from the open sets, so of X to the space of abelian groups. So to every open set, you associate an abelian group. So F, so U associate F of U, which is an abelian group. And so what you could think of is you have, for instance, a differentiable manifold, and you look at the differentiable functions on open sets. This is an abelian group. In this case, there's more structure, but anyway, that's it. Or you take an algebraic variety, you take the regular functions on the open set, that has this property. That's not quite a pre-sheaf, which has the following property together with what one could call a restriction map. So with maps of abelian groups. So whenever U is contained in V are open subsets, then you have homomorphism. So which I maybe call say restriction from V to U, although it's not necessarily a restriction, but you can think of the restriction which goes from F of V to F of U. So in simple cases, like if we talk about differentiable functions on a manifold, you just take a differentiable function on V and you restrict it to U. And so this gives me a group homomorphism. No? This kind of trivial stuff. So this is a pre-sheaf. So you have for every open set, you have an abelian group, and for every inclusion of open subsets, you have a morphism which behaves, well, with some properties, obviously, that if you restrict twice, it's the same. So if, you know, such a, if U is contained in V is contained in W, then, you know, restricting twice is the composition. So R, what is it? If you go from U to V, and you go from V, no, if you go from W to V, and from V to U, the composition is equal to the composition directly from W to U. Now obviously, this is the composition. It's kind of clear that if it was the actual restriction, this would be trivial. If you take a differentiable function and you restrict it from an open subset to a smaller subset, and then to a yet smaller subset, it's the same as if you would restrict it in one step. So that's a pre-sheaf. And a sheaf is such a thing which has some locality property. So it has two different locality properties. First, so the elements here, you would call the section, so maybe I should write that. This is kind of, so the elements S in F of U are called the sections of S on U, of F on U. So I call them sections. It's kind of, but you know, it's like in your case, in the case, in the example I said, it's just a differentiable function on U. I call this a section of the sheaf of differential functions on U. And now, the claim, what makes a sheaf is that the sections are local in two senses. That if you have an open cover of our space, then two sections are equal if and only if the restriction to each open set in the cover are equal. And secondly, if I have sections on each open subset of a cover with the property that on the intersection of the two, of any two of these open subsets they coincide, then this gives rise to a section of the whole thing which restricts to the sections given. So there are two things. So F is called a sheaf if first so if for every open cover whatever U alpha of X, we have the following. First, so I like to, so by abuse of notation, I want to say if S is an element in F of W, then I write S restricted to V for R W V of S. Okay? So I want to, so the intuition is that this is some kind of restriction, although here by definition it's just some arbitrary map. But I just, as an aberration, I write this.
What is R? You mean T?
R is this.
Okay.
I just change the notation. I just say I want to write it like this. Although it doesn't have to be, strictly speaking, the restriction. Although in many cases it is, but sometimes it isn't. I mean, in the example we have is just a restriction. And so if the following thing I have, so if so let S and T be elements in F of X. Maybe one needs for any U, but anyway, it doesn't matter. Okay, so yeah, I don't think so. I think I have to take some U, some open subset U, and I take a cover of U. So if I have S and T in F of U, such that S restricted to U alpha is equal to T restricted to U alpha for all alpha, then it follows that S is equal to T. So you can determine whether two things are equal locally. And the second statement is you can construct sections locally. So let S alpha be elements in F of U alpha for this cover. And obviously, you have for every open set of this cover, you have a section. Now you want to make one section out of all of them. Obviously, this can only be if on the intersection of the open subsets they are the same. So with for all alpha beta, S alpha restricted to U alpha intersected U beta is equal to S beta restricted to U alpha intersected U beta. Okay, if you have that. So where this restricted means always this idiotic homomorphism here, then it follows, then there exists an element S in F of U with F restricted with S restricted to U alpha is equal to S alpha for all alpha. So I can locally construct sections. And you can see, if you, for instance, talk about differentiable functions on a manifold, all these things are trivially true. So differentiable functions on a manifold, on open subsets of a manifold, form a sheaf. And in fact, the kind of algebraic geometry kind of way to do differential geometry would be to say that the natural thing how to describe a manifold is as a topological space together with a sheaf, namely the sheaf of differentiable functions subject to certain conditions. But this is not how differential geometers usually do. At least I don't think that Claudio does that. But but it's how one constructs these things. Okay, so that's all there is. And so, for instance, also for an algebraic variety, if I take the regular functions on open subsets, they form a sheaf. But you can look at much more general sheaves. So, if you take what is called, in differential geometry, if you would take a vector field, so to every point in your manifold, you associate a tangent vector in such a way that it is differentiable. You can do this on open subsets. Then vector fields also form a sheaf, and you can look at this, or differential forms. And there are much more general things that you can do which form sheaves. Anyway. And what?
It's not as complicated as expected.
No, it's by itself. You see, by itself, it's a completely trivial concept. Then you have to. It's true that by itself, it's just abstract, but it's not particularly complicated. Then, but obviously at this level of, then in the concrete case, if you want to work with it, you have to look at certain special sheaves with certain properties, and then it becomes more complicated. But at this level of abstraction, it is very simple and also quite useless because it's abstract nonsense. No? Now, however, it turns out that this language can be quite useful if you want to. Certain problems can be studied much better in this language. Note that you talk about sheaves. And it's just.
But do we gain anything by considering things in this generality?
Yes, you would. I mean, not in my course because I don't look at sufficiently difficult problems. But if you want certain things which are a little bit more difficult, you can somehow only understand in these terms. I think this is the modern language of algebraic geometry, and it's somehow. But it's not only. You also find in other sheaves are quite general. In modern in complex analysis, you would use sheaves, or also in quite a bit of analysis, you somehow use it. I mean, maybe not in the simpler things, but anyway. So it's just certain things. Here you just capture that you can associate to every open set. That some kind of functions on it, generalized functions which are local, and then there are extremely many examples of such things, and you have a common language for that. And then, however, if you want to apply it in any case, you have some very special sheaf which has some extra properties, and you work with that. So one thing is that if you have a sheaf, you have a corresponding associated cohomology of sheaves. And this cohomology of sheaves tells you also something about, if you want, it's often, one thing that you want is you want to construct some, you have a sheaf, you want to construct some sections, and the higher cohomology group tells you about some kind of obstacles which are in your way when you want to construct sections of a sheaf. And so you, for instance, therefore you have to study the cohomology in order to remove these obstacles. And so that it gives you a natural way to formulate certain problems in a way which makes it easier to solve them. But anyway, for us, we don't use sheaves. No, I mean, I maybe shouldn't have gotten distracted, but maybe you just. But anyway, this is this thing. It's a very standard thing. It's part of the modern language of algebraic geometry or complex analysis. Okay, let me go a little bit on. Where was I? Yeah. Yeah, but this was just the word I was using for fun. No? Yeah, well, and now I failed to scare you. Instead, I wasted some time. So now, but where was I?
So what is an invertible sheaf?
No, I will not. Is there something I can say? Well, we will, in some sense, when I get there, I will tell you. Okay. But because in some sense implicitly we talk about it, but not explicitly. Or maybe if I'm lucky, when we get there, you will have forgotten, and so I don't have to explain. So I said, yeah, I was in the middle of saying that. So see the curve. Two divisors D and E on C are called linearly equivalent. If D minus E is a principal divisor, so the divisor of the function, and this is denoted, that linear equivalence is denoted, D is linear equivalent to E. So, and I also write D for the linear equivalence class of D. So thus, the Picard group of C is just the group the divisors of C divided by the linear equivalence. So this pick C. So is the group of equivalence classes. Obviously, this is a group because this is also just the set of the divisors of C divided by the principal divisors. Which are a subgroup. We divide the divisors by the group of divisors by the subgroup of principal divisors. And so this is the quotient group. Now we only have B in groups here, so no problem dividing. That's the Picard group. And now I want to see, so there's two things I want to see. So for one thing, I want to see that principal divisors always have degree 0. And this means that I can also, that the principal divisors are actually a subgroup of the divisors of degree 0. You get pick 0 of C to be this quotient. And this actually is a very important invariant of C. So with a little bit of extra structure, C is up to isomorphism determined by its Picard in a suitable sense. So it's not, it contains a lot of information. No? Before, this divisor somehow is just kind of a stupid thing because there's no structure there, but once you do this, this quotient almost, contains in some hidden way all the information about C. But before that, I want to say how divisors behave under morphisms. So, to see how divisors behave under morphisms. So this is quite, maybe I will have to stop there, but anyway. So that is for a dominant morphism phi from x to c of curves and D in a divisor on C, we define the pullback. Phi star D, which is a divisor on X. So dominant morphism, the Algebraic dominant morphism means that the image is dense in X, but we are here talking about projective curves, so a dominant morphism is surjective, so it's just a surjective morphism of curves. But I mean, the standard word people use is still dominant, although it just means surjective. So, first we want to talk about the degree of this morphism. So, degree of a dominant morphism. So we had seen that if we have a morphism or even a rational map, we can pull back rational functions via this map. So therefore we basically have that the pullback of this. So first, if a morphism, so let me just remind you, so if P from X to C is dominant morphism, then P upper star from Kc to Kx is a homomorphism of fields. Easy. Field homomorphism. And the fact that this is dominant means that this is not the zero field homomorphism. So it is, homomorphisms of fields are either zero or injective. So this is an injective field homomorphism. So thus, if I take the field extension Kx over, so just write, I want to write Kx over Kc, which is supposed to mean Kx over P star of Kc. And just to write it shorter, is a field extension. Okay, so we have the rational functions on X over the rational functions on C are an extension of fields. And note that both X and C are curves. So these are two fields of transcendence degree, both of transcendence degree 1. So both X and C, Kx, and Kc have transcendence degree over K. Then maybe it doesn't directly follow, but I just tell you that it will follow from this that this is a finite field extension. So by itself, obviously, so basically if this was an infinite extension, one, basically by what we said before about the transcendence degree, it would follow that that Kx would have to be, so these are both finitely generated fields. So if you have an infinite extension of finitely generated fields, then it must have a positive transcendence degree. So therefore it follows that as this has dimension 1, the dimension 1 is equal to the transcendence degree over K. So both have dimension 1, therefore transcendence degree 1 over K. So therefore this is a finite extension. So thus Kx over Kc is a finite extension. And the degree of this map is the degree of this field extension. So we let the degree of phi is Kp equal to the degree of Kx over Kc. So that's the degree. Now, well, maybe I'm a bit, even though you fooled me into doing something else, I cannot go infinity over time. Let me see. Maybe I can just say with words, because otherwise it will be, you will be too much worried about when I will end instead of to listen to me. So, so now I want to see. So we can now we can define this pullback, and in particular, if you take, and the theorem will be that that if you have that under the pullback, the degree of a divisor gets multiplied by the degree of the map. So if you have a divisor of degree A here, and this map has degree D, then the pullback divisor will have degree A times D. In particular, this applies, but the pullback is just you take the points, you take the inverse images of the points with certain multiplicities. So in particular, if you just have one point, the pullback of one point is all the inverse images of this one point together with some multiplicities. So that means counted with multiplicities, the inverse image of a point in C is equal to this degree of the map. And one can actually prove, although we don't, that for a general point in C, all these multiplicities are 1, of the points. So that means that the degree actually just meant for a general point in C, the number of points in the fiber is this degree. So that is degree of the so this is the meaning of the degree. And so the difficult thing to prove here is that the degree multiplies in this way. This is the thing that we're not going to prove. An easy consequence of that will be that principal divisors have degree 0, as we shall see, and that we'll do next time. Okay. Yeah. So, maybe I should